Example 3. A manufacturer produces paper cups in the shape of a right circular cone with a radius equal to 1/4 its height. Let's write that down actually real quick. A radius equal to 1/4 its height. I just have a feeling that that might wind up being important. And then next, specifications call for the cups to have a top diameter of 4 centimeters. After production, it is discovered that the diameter measures only 3.8 centimeters. Use differentials to approximate the loss in capacity of the cup. Okay, well, let's start setting this up. We're gonna need the volume of a right circular cone, so that should be 1/3 pi r squared h. And one thing that we can do with this other relationship up here is we could maybe solve it for h, right? If we do that, we'll get h is equal to 4r, which then allows us to reduce the number of variables in this volume equation. So this is now v equals 1/3 pi r squared times h, which is 4r. And so we get v is equal to 4/3 pi r cubed. Now that we have our volume formula, let's see how we're going to relate this to differentials. So if you just think about that differentials formula, it was what df is equal to f prime of x delta x, or dx. And for us, it's going to look like dv is equal to v prime of r dr, okay, or delta r. Right now, well, this means we're going to need our derivative of v. Let's go ahead and compute that. So v prime of r, well, you just bring down that 3, right? So you'd have 4/3 times 3, which is just 4, and then pi r, and if you reduce the power by 1, that's to the 2. And after doing related rates, some of you might be wondering, well, why isn't there a dr dt here? And that's because we weren't differentiating with respect to t. We weren't expecting that this volume here was changing with time. We differentiated with respect to r. So we got that now. And this means we can actually use this formula here. So we'll have then dv is equal to v prime of r, so that's 4 pi r squared. Well, the question is well, what is r? Okay. Well, it's this 4 centimeters here, 4 centimeters. But that was for actually our diameter, not our radius. So actually our radius there would have been actually 2, wouldn't it have been? Okay. You might be wondering why I chose to use r equals 2 centimeters over r equals 1.9 centimeters here in this formula. Okay. And the reason is when we're going to compute this change in volume, we want this calculation to be as easy as possible. So we're going to plug in the nicer number here, 2. The only thing that we're missing is the dr here, okay, just dr. Okay. Well, is what we need there is the change in the radius. So we know that at one point here we have a 2 centimeter radius, and at another we have a 1.9 centimeter radius, right? We're just dividing each one of these by 2 since they're the diameter. Okay. So the change in r is 0.1 centimeters, going from one to the other. Now the question is should it be 0.1 or minus 0.1? And here's what's going to kind of give us an idea on that. We're going from 4 centimeters to 3.8 centimeters. That's a decrease. Okay, so what that means is this dr needs to be negative. So we're going to have minus 0.1. Okay, and if we go ahead and we multiply all this together, minus 1.6 pi. And you can check, you can go and compute that actual change in volume, and what you'll find is it should be pretty close to this minus 1.6 pi. And if we were looking for units here, this is a change in volume, right? So we saw we were measuring these lengths in centimeters, so we'll be measuring the volume in centimeters cubed.